What's up, everybody? Welcome to lecture 16 over section 3.1. Today's lecture, we're going to start off with two different definitions. The first one is of the ideas absolute max and min, and the second one is of the idea local max and min. And there's going to be some similarities between the two definitions, but they are different and they do have very different implications. So to start off with, the idea of an absolute max and an absolute min. Starting with this first definition of an absolute max, we say that our function f has an absolute max at c if f of c is larger than or equal to f of x for all values of x in the domain of our function. So that's what this here is saying, x in the domain of f of x. Here we have c in the domain of f of x. In other words, if for all values that you could put through your function, if f of c is larger than or equal to every other value within that domain, or rather is larger than f evaluated at any other value within that domain, then we say that our function f of x achieves a maximum at x equal to c. On the other hand, the idea of absolute min is just the reverse. Instead of saying f of c is larger than, for the min, we're going to say that f of c is less than or equal to f of x for all x in the domain of our function. In other words, what we're getting at is if there's a particular value where your function is the largest it could possibly be or the smallest it could possibly be within your domain, well, then that's going to be your absolute max or your absolute min accordingly, right? On the other hand, though, we have this idea of local max and local min, and this gets a little bit more finicky. So for a value c, for your function to have a local max at a value x equal to c, what we're saying is for all of those x values immediately around that c, then f of c is going to be larger than or equal to f of x. And I actually have a typo up here on the board. This should be c minus epsilon or c plus epsilon. Now what I'm saying here is you're going to take c, and you're going to take a collection of numbers around c. If for every value of x in that collection, f of c is larger than or equal to f of x, well then, f of c is a local max. Or another way of saying that, your function achieves a local max at the value c in the interval c minus epsilon, c plus epsilon. On the other hand, we have the idea of a local min, which again, as with the difference between max and min, or absolute max and min, the difference between local max and local min is just going to be that the inequality flips, but everything else is the same. So absolute max is just that there is no other x value that gives you that large of a value or larger. Rather, there is no other x value that gives you a larger x, or I mean a larger y. Similarly, absolute min is the idea that there is no other value of x such that your function evaluated at that will be less than what you're getting. Does that make sense? I hope that makes sense. If it doesn't, by all means, shoot me an email, we can clarify it. Whereas on the other hand, local max, local min, what we're saying is take that particular value, jiggle your x value, right? So jiggle x equal to c, and look at the values immediately around it. If your function achieves a value larger than f of c or smaller than f of c, then it's not a local min or a local max. That's all we're getting at, is that in a small interval around that c value, you've hit either your max or your min. Having said that, let's see this in practice. Now, to see these two ideas of local and absolute extremums in practice, we're going to consider these two examples behind me. First, here on the left, we've got the function 3 times x to the 4th power minus 16 times x cubed plus 18 times x squared, where x is between -1 and 4, including -1 and 4. So it's on a closed interval from -1 to 4. Searching for a local max, we have one point that jumps out right away. This point here, at x equal to 1. And the reason why is because you look at that point and you jiggle it. So you take 1 and you look at the immediate points around it. So at 0.99, at 1.01, in that sort of scale of points, there's no other value of x that produces something larger than 5. So just take, like I said, a collection of those values, jiggle your x around 1 within that collection. If you get a number bigger than, then you're not at a local max. But in our case, everything is smaller than every value of x. Our function gives us something smaller than 5, so that must be a local max. Now, on the other hand, we might look at the extreme, or at the endpoints and say, well, aren't those local maxes too? No, not really. We don't really consider them local maxes because local maxes occur on what are called open intervals. These things are closed. We don't have a value that we can jiggle to the left of -1 or to the right of 4. So we just don't consider those local maxes. But we do consider x equal to 1 or -1, y equal to 37. We do consider that point an absolute max because in that interval from -1 to 4, including -1 to 4, your function doesn't produce a number bigger than 37. Meanwhile, let's consider the absolute mins. Well, we just said this point's an absolute max, so it can't be an absolute min. What about this point over here? Doesn't make sense to call it an absolute min because this thing down here is way smaller than it, right? So we would call this point way at the very bottom, 3, -27, an absolute min. But it's also a local min of our function. And we can see that because if you were to jiggle 3, your function would produce numbers that are larger than -27. So this has to be in a trough down here. Meanwhile, we have another trough at the point 0, 0, meaning it must also be a local min. So you can have multiple local mins. And so far, we've only seen one case where there's one local max and one local min. Or I mean, one absolute max and one absolute min. So you can have certainly multiple local maxes and local mins. Those are just troughs and peaks, right? But what about cases with multiple absolute maxes and absolute mins? Well, we can see that here in this example of cosine of x equal to g of x. In this function, we've got a bunch of local maxes. In fact, we have a local max at every value of x which is an even multiple of pi. So at 0 pi, 2 pi, 4 pi, so forth and so on. But we also have local maxes there, so absolute maxes and local maxes at the same spot. Meanwhile, we have the same thing occurring for our local and absolute mins. Those have multiple occurrences, right? At every value of x equal to an odd multiple of pi, so 1 pi, 3 pi, 5 pi, so forth, so on, all of those values are going to give us local and absolute mins. So we can have multiple maxes in both sense, both in the absolute and the local sense, and we can have multiple mins in both sense, the local and absolute sense. Having said that, let's take a minute to notice something about all of these. Everywhere we have a local max or a local min has to be a peak or a trough. Well, isn't that the same thing as saying the tangent line has to be perfectly horizontal? And if the tangent line is perfectly horizontal, doesn't that mean it has a slope of 0? And if it has a slope of 0, doesn't that mean it has a derivative of 0? Then our function should have a derivative of 0 at those x values? Look at what happens to the derivatives of this function at x equal to 0, x equal to 1, and x equal to 3. Take a couple seconds to yourself and think about that. Well, the derivative of this thing is going to end up being 12x cubed minus 3 times 16x squared plus 36x. And we could play with it, and we would find that, yeah, in fact, each of those local max and mins, our function has a derivative of 0. What I'm hinting at here is what's called Fermat's theorem. Not to be confused with Fermat's last theorem. That is infinitely more, I should not say infinitely. It is vastly, hugely more difficult to prove than Fermat's theorem. So give me just a second and I will write that out on the board. In the meantime, check those derivatives for yourself. Check out the derivative of f of x and check out the derivative of g of x. See what happens at those local maxes and mins. So Fermat's theorem, properly said, states that if f has a local max or min at x equal to c, and if the derivative of f exists at c, then that derivative has to be 0. Now to see this in practice, let's consider the function x squared. We know the derivative of x squared is 2x. And we know that x squared has a local minimum at x equal to 0. Well, just checking then that the derivative at x equal to 0 is equal to 0 is pretty trivial, right? Just 2 times 0, that's 0. Excuse me. So it must be that this is an application of Fermat's theorem. Cool. All right, that was straightforward and easy enough. On the other hand, check out the absolute value of x. The derivative of that thing is going to be 1 for x greater than 0. It doesn't exist when x is equal to 0, and it's equal to -1 when x is less than 0. But we know the absolute value of x has a local minimum at x equal to 0. So we can't apply Fermat's theorem here, is what this is getting at. Another way of looking at this is that Fermat's theorem is hinting at an idea for us. It's suggesting a possible test to find your local maxes and local mins. What it's suggesting is if you were to take the derivative of a function and then search for all values of x where that derivative is equal to 0 or doesn't exist, those are possible candidates for a local max or a local min. Having said that though, let's keep chugging along and check out the next definition. Now this idea that I was just hinting at is the idea of what's called critical numbers. Critical numbers are any value c in the domain of your function f of x such that the derivative of your function at that value c is equal to 0 or it does not exist. And when applying these ideas, all we're going to do is we're going to take the derivative of a function. So consider this example here, x cubed minus 3x squared plus 1 is equal to f of x. The derivative of that thing is 3x squared minus 6x, which we can factor out to be 3x times the quantity x minus 2. Now to find its critical numbers, what we're going to do is we're going to set this thing equal to 0. Why in this particular case am I saying we only need to check for where our derivative is equal to 0? Well, it's because our derivative is a polynomial, right? So its domain exists everywhere. Hence, there are no values of x for which the derivative does not exist. So all we need to do is check where this derivative is equal to 0. Well, in this case, that's pretty easy, right? Once we have it factored out, we can see that our critical numbers are going to be where x is equal to 0 or where x is equal to 2. Dope. So, c is equal to 0 or c is equal to 2. Both of those are critical numbers. Awesome. So we just found all the critical numbers for that first function. Now on the other hand, let's consider the function x raised to the 3/5 power times the quantity 4 minus x. And when we take the derivative of that thing, after we do some algebra, what we get is the quantity 12 minus 8x divided by 5 times x raised to the 2/5 power. Okay, well, this thing has both cases, doesn't it? It has a case where that derivative won't exist. Like there's a value of x in the domain of your original function for which that derivative does not exist. There's also values within the domain of your original function where the derivative is equal to 0. So what we need to do is identify how to find those. Well, since this thing is a rational function, since the derivative is a rational function, to find out where that derivative is equal to 0, all we need to do is consider where that numerator is equal to 0, right? Yeah, absolutely. That's the whole thing with rational functions. That's convenient. So we're just going to set that numerator, 12 minus 8x, equal to 0. And when we do, we're going to find that x is equal to 3 over 2. So one of our critical numbers is equal to 3 over 2. Now in the case of where our derivative does not exist, well, that's just requiring us to go find when our denominator is equal to 0, right? And our denominator is equal to 5 times x raised to the 2/5 power. Well, that's convenient because that thing's 0 whenever x is equal to 0, right? So our other critical number is going to be 0. And that's all we're going to do to find our critical numbers. We're just going to take the derivative of our functions, set them equal to 0, and find out for what values of x in the domain of our original function does our derivative not have a value for. So for what values of x in the domain of our original function does our derivative compute does not exist? And for what values is it equal to 0? And that's it. That's all she wrote. That's all there is to it. Having said that, let's check out some more. Now to wrap everything up, I just wanted to end on this idea of how to find absolute max and mins in a closed interval from A to B, assuming your function is continuous. That is to say, assuming you're given a function f of x and it's continuous on a closed interval from A to B, to find the absolute max and min, you follow the following process. First, you don't want to find the critical numbers of your function within that interval from A to B, but this time it's going to be the open interval, right? So you're not going to include those endpoints. Then, you want to take and you want to find out what your function is evaluated at those critical values, at those critical numbers. In other words, find those critical numbers, then find out what your function is at those critical numbers. The next step is to find out what your function is at x equal to A and at x equal to B. From there, you're just going to pick the largest and smallest values accordingly, right? The largest value will give you your absolute max. The smallest value will give you your absolute min. That's all there is to it. Having said all of that, I am going to let y'all go. Started this lecture at 11:30 p.m. It is now 1:15. So I'm going to let y'all go. I'm going to go home and chop this video up and post it tonight. So another hour's worth of work probably. Enjoy, have fun. If you have any questions, by all means, shoot me an email, come by office hours. Office hours are, of course, Mondays and Fridays from 4 to 5, I believe. I've got a Zoom link set up, or you can come by my office. Yeah, whichever is easiest. But have a good one, everybody. Later. I'm going to bed.